Since we're running so far over time already, I'm going to try to accelerate it just a little bit and get the session started. Poor memory, so I don't remember who's first, but Holger is already waiting in the wings there. We've heard already that technology is what moves ahead many areas of science, and same is true in Cryo-EM. This session is devoted to touching on some of the issues of technology development, not all of them, but some of them that we hope will move Cryo-EM forward in the next 50 years. First speaker, my colleague Holger Mueller, will be talking about laser phase plates. Thanks.
Thank you. I have to admit I'm a little nervous because although I've given talks like this several times, I've extremely rarely given them in front of my own group and in front of Bob. So please support me. So in 1959, Richard Feynman said in a speech at Caltech that we physicists should be helping by making the electron microscope 100 times better, but unfortunately he didn't say how. And then Cryo-EM came, better cameras, and so on. And about 50 years later, Bob said, let's make a laser faceplate. So this is what we're trying to contribute. Single particle cryo-electron microscopy is growing very well, and it's now the new method to get atomic resolution structures of biological macromolecules. And we all want cryo-electron tomography to grow equally fast. What makes this hard? Well, radiation damage means that images can't be exposed enough to get a good signal-to-noise ratio. The result is we need to average tens of thousands of particles when in theory, as Richard Henderson showed beautifully, a much smaller number should be sufficient. And in tomography, you need to split the already small dose into several steps, which is extremely hard. In light microscopy, Fritz Zernike invented phase contrast in the 1930s as a way to increase the contrast and therefore the signal to noise. And implementing that in electron microscopy is the topic of the talk. The most successful way of generating phase contrast in electron microscopy so far is the Volta faceplate. So how does phase contrast work? And I'll spare you the physics lecture, but in the back focal plane of the objective lens, you can imagine that the electron beam is divided in two parts. The first one is the part of the electron wave function that was not diffracted by the specimen, and those come to a focus at the center of the back focal plane. And the second part is the electrons that did get diffracted, and they form a disk around that center. Phase contrast is generating by causing a 90 degrees relative phase shift between the two parts of the wave function. So I need to phase shift the central part, but not phase shift the surroundings, or vice versa, but 90 degrees is what we need. Okay. In the Volta faceplate, this is done by inserting a carbon film in the back focal plane, and when the electron beam hits the carbon film, it locally modifies its properties so as to generate the phase shift. But the problem is that the effect isn't well calibrated. So as you start it, the phase shift builds up and then eventually exceeds the 90 degrees that you want. Then you need to find a new spot on the faceplate and the process starts again. And each time you move the faceplate, you slightly change the properties of the microscope. And notice that the phase shift varies very strongly over the time needed to take your data. So you don't have a microscope with constant properties as you want to later put the data back together and get biological results from it. Nevertheless, the contrast increase is very obvious, and so phase contrast seems to be the way to go, but how to make it more stable? So the idea is to focus a laser beam so that the laser focus overlaps with the electron focus, and then there's the so-called ponderomotive interaction between the laser electric field and the electron that generates the phase shift. Again, I'll spare you the details. Suffice it to say that since we're not bringing any material into the electron beam, There is no material that can accumulate charge or suffer radiation damage. And since the properties of the laser beam are determined by Maxwell's equations, this should, in principle, be very well controlled. So what's the snag? The snag is you need to focus 75 kilowatts of laser power to a few microns in order to get the 90-degree phase shift. Just to put this in context a little bit, this is a 10 kilowatt laser used for cutting and welding. It will cut to 1 inch of steel, and it's not powerful enough. You need 7 or 8 of those. This is a military laser designed to do damage to stuff, and it's not powerful enough, and it's potentially unsafe. So what are we to do? What are we going to do is recycle the laser beam. So this is a schematic of the whole thing. The electron beam starts at the top, goes to the bottom. The specimen is here. The back focal plane is here. That's where I would love to put my laser, but there isn't enough space over there. So we use the Lorentz lens to generate a magnified copy of the back focal plane here, and that's where we put our laser. We also put 2 extremely high-quality mirrors to bounce the beam back and forth 10,000 times, so that 10 watts that bounce around 10,000 times build up to form a 100 kilowatt standing wave here. And that is the brightest continuous wave laser spot ever made. So this is no joking matter. And it phase shifts the electron beam here. Early on, we found we can sustain this power until we turn it off. We've never seen any degradation of this system. There's a lot of engineering that goes in here. You need to control the thermal expansion of the mirrors, and you need to keep the mirrors extremely, extremely clean. The tiniest speck of dirt will burn in and ruin the mirror. But what we've sometimes found is that a new mirror will burn when you bring it to high power the first time. But once you've brought a mirror to high power, it never failed on us after thousands of hours of operation by now. Okay, so in principle, this could have near ideal properties, but we need the relay optics. We need this extra lens and then another lens that we call the X lens to relay the image through the system. And those lenses we will have to talk about later because they cause extra aberrations that we don't want. With that being said, this is what it looks like. It's down in the basement of this building. We can take a look later if you want. This is a low-base Titan 80 to 300 kilovolt microscope that Bob brought to Berkeley before I was here. We've attached our laser optics to the left and to the right, and this is the faceplate module which contains the extra lenses and the laser cavity where the beam bounces back and forth 10,000 times. A few years ago, we asked Yifan Cheng, who's in the audience here, and he was happy to give us some frozen grids of proteasome particles and of Rubisco, and we took our first really successful phase contrast images that made us extremely happy. We could generate a atomic resolution reconstruction from these images. Everything seemed nice until we looked a little closer, and we found that there were performance limitations. Some we expected. We did expect chromatic aberration and spherical aberration from those extra lenses to be a limiting factor. But the resolution was much worse than we thought it would be. And so we didn't get any record in terms of how many particles we need, what resolution we get, or maybe even solving a particularly hard particle. None of that, unfortunately, happened. So chromatic aberration was a problem as expected. Ice contamination was kind of expected in the old microscope, but it was much worse than we thought. And the surprise was Johnson noise. So what happens there? When the electron beam goes through the laser cavity, there's a hole in the metal walls of that cavity. And this hole was only 2 millimeters large. We didn't know a reason to make it larger. We thought 2 millimeters is plenty. That metal is full of room temperature electrons that move around with their thermal energy, and that generates magnetic field fluctuations that slightly blur the image. So to overcome that, we simply had to make the hole larger, but this laser cavity, it looks simple, but it's really a watchmaker's job. It contains several extremely precisely machined parts. So it took the machine shop several months to do that, even though it was during the pandemic when the machine shop wasn't particularly busy. Anyway, with that larger hole, now the contrast transfer function envelope agrees with theory, and you see the blue dotted line is theory without a faceplate, and the red line is what we actually get with the large hole, so it barely degrades. So this is where we want to be. And now and we also did something about the ice contamination, and now the performance was only limited by chromatic aberration as expected. So this is the laser on. We get 2.8 angstrom resolution with 15,000 particles. Again, no record because of the chromatic aberration, but as good as we could expect given the chromatic aberration. Comparison with the laser off gets a better resolution because here we could turn the transfer lens off and get rid of the chromatic aberration. Okay? But basically it works. The good news is the phase shift was found to be ridiculously stable. So over 10 hours, it doesn't show any systematic drift. It doesn't show a lot of variation. In fact, most of the variation here is probably noise in extracting the phase shift from the images that we took. So that's nice. And the chromatic aberration problems hopefully will be overcome with the new microscope that is being installed in this building right now. And as of 2 days ago, we got a beam down. So keep fingers crossed that this will work very soon. It has a cold field emission gun to overcome the chromatic aberration problems. It also has a slightly lower chromatic aberration than the Titan by some redesign. Electron optics has automation features, so we can go through lots and lots of specimen, and has a spherical aberration corrector. And why we want that, I'll explain later. So this is going to be nice. And summarized here is a plot of the contrast transfer function of the old microscope. You see at high spatial frequencies, the contrast is gone, and this is what the new microscope should give us, which goes to very high spatial frequencies. In fact, this should give a resolution of 1 angstrom, where the CTF is still 50%. What's with this streak here? Well, that's from the one-dimensional shape of the laser beam. And we're working on a dual faceplate where 2 laser beams are present. Now we have 2 streaks, but each of them is only a quarter as pronounced. So overall, we're winning. Okay, the faceplate for that new microscope has been built. This is a picture taken yesterday. It sits down here and is waiting for installation. It's been tested on the optical bench and is working fine. So keep fingers crossed that this will go into the microscope soon. In the meantime, what have you found out? What have we found out can we do with phase contrast? So this is again some apoferritin and some rubisco. And the first thing you notice, if you just look at this by eye, the apoferritin particles all look very different. There are disks, there are crescents, there are rings. And this variation is much stronger than what you would expect from just the fact that they all have different orientations. So what that means is the faceplate enables human intelligence as well as artificial intelligence to spot variations between individual particles and not just class averages. That's a nice thing to know. But of course, what you really want to do with phase contrast is tomography. So how does a cell biology sample look like when imaged with phase contrast? And can you actually do tomography? Well, we found this is first example of a cell bio specimen. These are human skin cancer cells de-roofed. So you see all those fragments of the cell here. This mottling is probably the ice. For a short time, we thought maybe these are ribosomes, but it's probably just structure in the ice. And this is the same specimen imaged right after that without the laser. And it's not a totally fair comparison because this is when the specimen was fresh. This is when it was already exposed once. But very clearly, you can see how the contrast enhancement helps here, right? Okay. But how about tomography? The problem with tomography is that we need to tilt. Whenever you tilt the specimen, in theory that should just work. In practice, the specimen might be charged a little bit, and when you move the charged plane through the electron beam, it might deflect the beam a little bit. In a standard microscope, that's not a big deal, but with phase contrast, if the beam gets deflected, it might no longer intersect with the laser, and then the advantage of phase contrast is gone. So we worked a lot on automated alignment between the laser beam and the electron beam. And this is a simplified picture, but essentially what we do is we deflect the electron beam next to the hole that we want to image so that we don't pre-expose the specimen. And then we change the illumination conditions to generate a so-called Ronchigram. This is just a magnified electron micrograph of the laser beam. And by fitting this pattern, we can tell what the relative alignment of the laser and the electron beam is. Then we apply corrections, and then we move the beam into the hole and take our image. With that, a first thing we checked was if you have phase contrast, you should be able to align the frames using a much lower dose per frame than without the laser, and that should enable you to do better motion correction. And that indeed is the case. So with the laser on, we can identify the individual particle locations with a RMS deviation of a little less than half an angstrom, and if the laser goes off, then it's more than 1 angstrom. So you can get better motion correction and therefore hopefully better quality data. If you look at the raw data here, the difference is even more striking. So on this grid, we have plotted the local motion of particles. This motion is exaggerated, I think, 20-fold. My group is in the audience. They can correct me on this number. And this is with the laser off, and you can see that almost all the time, the correction actually fails. We are not able to see how anything moved on this one. So this is a nice advantage. But can we actually do a tilt series of this? And so we tried that out on the old microscope. This was a true tour de force that hopefully we won't have to do again, because hopefully we'll have the new microscope, which makes that much easier. But this is a Rubisco grid just as a proof of principle, not a fib-milled lamella, and things may be slightly different in fib-milled lamella. Anyway, minus 57 to plus 57 degrees with 2 electrons per angstrom squared per tilt angle. And here's just one of them with laser off versus laser on. You see the black spots are gold fiducials. And then we put them together. Can I start this? If I see my mouse pointer, then I can maybe start this. So yes, this is going through the specimen in Z direction. And you see that now we're in the bulk, and now we're reaching the back surface where all the particles are. So this is, of course, a small step for humanity, but what it does show is that we can keep the laser aligned throughout a tilt series. With a fib-milled lamella, the problem may be harder, because in these grids, there's always a conductive carbon surface close to anything you want to image, so that charging may be slightly alleviated, whereas in a fib-milled lamella, the problem may be harder. We might have to overcome that with carbon coating or something like that. We'll see, but so far, so good. So this is what we've seen, right? The particles concentrate on the perimeter here, and then there's very little in the bulk, and then when you hit the back surface, there's more particles there. Okay, last thing I want to say, with the faceplate, you can, in principle, get rid of defocus and image at 0 defocus, and this is a pure theory plot, just integrating contrast transfer function over all spatial frequencies, and you see that, in principle, you get almost twice the information when you're at exactly 0 defocus. So that's maybe a long-term goal for us, and initially, we'll just do the low-hanging fruit, but that's what we want to do in the long run. If that happens, then nearly 100% of the information that is in the electron beam gets delivered to the camera, and then with a very good camera, you can get it onto your hard drive. We're working with the Chan Zuckerberg Institute for Advanced Biological Imaging on developing the crossed faceplate that I mentioned makes the contrast transfer function even better by removing the streak or making it less pronounced, right? So this is working very well right now, and they have a microscope with a faceplate in Redwood City. They expect to install the faceplate very soon, I think even on Monday. We're also working with Thermo Fisher to transfer the technology, and I have to thank, I already mentioned Bob Glaeser, who started this work. I cannot thank Eva enough, who helped us countless times behind the scenes, often without even telling us. Some problem just disappeared, and it was Eva who did it. We recently recruited some biological expertise, but this is a picture taken yesterday. So here's Peter, Jesse, Ian, Remis, Eric, and Hang. I have the privilege to work with a fantastic team, and the first people to make it work were Osip and Jeremy. And thank you so much for your attention.
Realize I have to get up again. So
with a tilted specimen, you have part of it is over focus and part of it is under focus, but it's stable enough that you can CTF correct by strips in the image. Is that how you would correct?
So for standard faceplate operation, this will be no different from standard tomography, right? You would just use the data, hopefully taking advantage of the increased contrast. But of course, you can't get the whole specimen to zero defocus. So that will be impossible in a tilt series.
Right, thanks very much. It's a great talk. I heard it in my time, getting better and better. So I'm just thinking whether there's any advantage if you can tune the amount of phase shift. Depends on the purpose of the experiments. If there is good reason to it, is it possible to do it in the near future?
Yes, so is it possible? Yes, it is possible. The highest phase shift we've ever generated is 135 degrees, and doesn't seem to be an obvious end to that. We could go even higher. So what can you do with a variable phase shift? If you can toggle it on and off, you can make an exit wave reconstruction. What we have to do in order to achieve that in practice is to make the faceplate switchable fast. Right now, it takes us a few minutes to ramp up the power. Eric here is probably going to undertake this. Another thing you can do if you can continuously tune the phase shift, there are proposals to, I think it's also amounting to exit wave reconstruction. You can essentially simulate a Fourier transform of the data and get both the phase contrast and the amplitude contrast out. And the final answer is if you have a given amount of amplitude contrast and phase contrast, in theory, there is an optimum phase shift where the two add in the optimum way. So this can be done and is an important thing to work on.
Alexei has a question.
For thin specimens without tomography, how would it go if you wanted to go to lower voltages and combine sort of the advantages of a low voltage instrument with a laser faceplate? Would, I don't know, the cost go down dramatically because the laser doesn't need to be as powerful and stuff like that?
In fact, the first phase contrast images we ever taken were at 80 kilovolts. It was a heck of a job to tune the Titan to work at 80 kilovolts. So you need lower laser power. Everything gets easier at lower voltage. Will it get much cheaper? Probably not, because you still need this enhancement cavity and you still need a microscope that's prepared to accept it. There is, however, a project to shrink the faceplate a lot. It's not close to being done, but if you can shrink it so much that you no longer need a heavily modified microscope, that'll make things easier. And OSIP, who's pictured there, is working on that.
Perhaps we'll just move on to the next. Thanks, Holger. Among the technologies that have dials that you can tune to try to improve things, one of them is the specimen temperature. That has a long and illustrious history behind it, and was in bad repute for a while, but Chris has picked it up again and done a very thorough job of characterizing, and looks like there is a pretty reasonable hope that that's something that will be useful in the future.
Right, thanks very much. Thanks to everyone for coming today and for inviting me to come and join in this wonderful event. Yeah, so as Bob said, I'm not going to give an overview talk today. I'm going to talk about one problem that we've been working on for quite some time now, which we think is important, and it dates back to the very beginnings of our field. And in particular, these two papers, I think, one of which was already mentioned today more than once, had a big influence on my thinking about this. And this first one here from Bob is a beautiful expression of the problem of our field, which is that as soon as we put any kind of high-energy beam on a biological specimen, it is destroyed. And it's destroyed in interesting ways, but this is the limitation to all of our work. And it was very early recognized that one of the things that you could do to, as Bob said, turn the knob on a microscope or any other experiment to try and make this not so bad is to lower the temperature. And of course, this, famous paper is the first demonstration of how this cryoprotective effect may be used to help us solve structures in biology. And so really, this does date back to the early days of the field. How low is low enough? How much benefit do we get at a given temperature? And it turns out that actually the physics of what goes on when you lower a specimen temperature is very complicated. And there are a lot of things that happen besides just the reduction in the fading of diffraction spots. But let's just look at those diffraction spots to start so you understand what we're talking about. So these are two electron diffraction patterns of purple membrane that start out nicely extending out to high resolutions around 3 angstroms. You can even see the water ring. And at 77 Kelvin, you can see that they fade significantly faster than at 13 Kelvin under the same irradiation conditions. And this is a direct evidence for the fact that the effects of radiation damage are being reduced at these lower temperatures. The primary radiation damage process itself, we don't think this is making any difference to that, actually, because a 300 kilovolt electron or even a 100 kilovolt electron can easily break any bond in any molecule. I mean, these are vast amounts of energy compared to the energies that are holding atoms together. So that's not the thing that's happening here. The thing that's happening is that we're stopping the breakdown products from moving away from where they were to start with and causing even more damage. And I think, it's a hand-wavy explanation, but you wouldn't go too far wrong in thinking about all of the benefits we get from cryo-EM coming from the fact that we're actually caging and trapping and stopping these intermediates from going any further and causing any further trouble. So this is there's a long history in this field of trying to understand this. And when we started out on this about 7 or 8 years ago, we thought, okay, the people have all abandoned liquid helium microscopes in cryo-EM. And why have they abandoned them? They've abandoned them because when you put your specimen in and you go to helium temperatures versus nitrogen temperatures, the images were always worse at nitrogen temperatures. But if you go back and look at just diffraction work, oftentimes the images were much better. Some of the highest resolution electron diffraction structures like aquaporin and others were all done using liquid helium microscopes. So what is going on here? Why is it that you can do so well with diffraction, but you can't do it with images? And that's what we sought to try and figure out about 7 or 8 years ago now. But the start of this was to see a consensus value for how much difference did you see in 2D crystals between liquid nitrogen temperatures, where things fade at about 5 or 6 angstrom squared per electron per angstrom squared. This is a B factor now. And at helium temperatures, it's another factor of 2 less from lots of measurements from all the way back. But as soon as people had these microscopes in their hands, they would do a comparative experiment where you would image at both temperatures and you'd find that things were worse. And one of the reasons things were worse is because buckling of the specimen, which occurs as soon as you put the beam on, actually becomes significantly worse at lower temperatures. And in fact, lots of things become worse at lower temperatures because a lot of specimens that are once semiconducting or conductive at room temperatures all of a sudden become insulating. So there's charging to worry about. And then there's this other thing that was noticed by several different observers, in that if you take amorphous water ice that's been plunge frozen as we normally do, and you look at a diffraction pattern for it, it has this ring at 3.7 angstroms, just like you always see. And, but as soon as you start irradiating, that ring actually broadens out and shifts. And this was attributed to a phase change in the water layer that happens upon irradiation, that somehow the water actually changes phase from being low density amorphous ice, which has a density of 0.94, to high density amorphous ice. And the first person to suggest this mechanism for what was going on was Haida, actually, in this paper here. And you can see clearly he measured the shift in the electron diffraction pattern, and he said that at temperatures lower than 70 Kelvin, water can be transformed, and it shifts, and that's the explanation for this shift. And then, a shift in density between 0.94 and 1.2 is a big change and can cause all kinds of problems. So I think the combination of this idea or explanation of what was going on at lower temperatures and the fact that nobody could get better data at helium temperatures on any of their microscopes using images, not diffraction, meant that everybody gave up on this. But we didn't give up on it. And the best people have done to date in attempting to make these comparative studies is this paper from Werner Kuhlbrandt's group, Olivia Field-Gardner, and she did a comparative study at nitrogen temperatures and helium temperatures of apoferritin, and in the end, they found that the structures are perfectly good, but they get to about the same resolution with the same number of particles at both temperatures. So you don't get this factor of 2 improvement that you might hope for. And why didn't they get the factor of 2 you might hope for? Well, it turns out that the movement at these lower temperatures, or what they thought would be the movement at the lower temperatures, was significantly more than it was at nitrogen temperatures. And we're able to do these kind of studies now where we couldn't back then because we have, of course, direct electron detectors that allow us to fractionate the dose and see what's going on. So we said, okay, from the fundamental physical perspective, if the radiation damage is less, we have to have this. And if it really is some fundamental process that's stopping the images from being better, then okay, but we need to know what that process is and we need to understand it. And so we pulled, the rug was pretty full under it, and we had to peel up the rug and find out all the things that were swept under. And to do this, we had to take an old microscope because they're not making modern helium microscopes anymore, although that's recently changed. And this is a Polara, which is almost 20 years old now. We bought it new at the LMB. And we had to get it back up and running into a reasonable level of performance. It turns out it is quite a good microscope once you put it in a nice box and you fix all the problems, and you can go from something that looks like this, which is where we started, to something that looks like this. So we were happy that we could actually use this to do some of these studies and start solving structures, but it took a hell of a lot of work to actually figure out what was going on. So the first question was, is this shift in the diffraction pattern real? Does it happen? It's been published several times, but we wanted to reproduce it ourselves, and so we did. And you can see it is absolutely observable here. So at 0 electrons per angstrom squared and at 14 Kelvin, you see this nice 3.7 angstrom ring. And then as you increase the electron fluence, that ring shifts its peak position and broadens out. And if you look at this plot, you can see that quantified as a function of temperature between 13 Kelvin all the way back up to close to liquid nitrogen temperatures. And it's interesting to see that actually, once you're up at 60 Kelvin, there seems to be no shift or very little, and down at 13 Kelvin, you get a very significant shift. Okay, so the observation in these previous papers is certainly reproducible, but is this actually a phase change? Is the density of ice getting higher? And the answer is no, it's not. And we did a lot of work to be certain that we're right about this, because we knew it was going to be controversial. And we also wanted to make sure we were right. So the first observation that we did to actually determine that this is not a phase shift is to look at energy loss spectroscopy. So this is an electron energy loss spectra, where you take the electrons that have gone through the specimen and you measure their energy. And in this case, 0 means 300 keV, and 10 would be 299.99. You get the idea, right? So, and most of the energy loss spectra from amorphous water ice is in this sort of low loss region here. We call it a plasmon, although it's not. It's sort of a heavily damped plasmon. But this heavily damped plasmon should be dependent upon the electron density. In other words, if this peak position shifts, then we know that there's a change in density. And if you look here, you can see that this peak position, as a function of temperature, doesn't move at all. And that is entirely inconsistent with a change of density of 20%. So those two facts cannot both be true. The second piece of evidence that we used to be certain that this is not a phase change is to actually track gold nanoparticles in the amorphous ice. So you make a specimen like one of the ones that Holger showed, where you have lots of gold nanoparticles inside, and if the density changes by a factor of 20%, they should move apart, right? That's what it means to change in density, right? There should be expansion. And again, we did not see that. So, and we didn't see that at tilt either. So essentially, it's not the case that that the shift in the diffraction pattern is due to a phase change in ice. This cannot be true. So what is going on then? Well, it turns out there has been work on this in other fields, and this paper, I think, is an absolutely critical one to understanding what's going on. And what you can see here is this is an experiment that was done by using X-ray spectroscopy on low temperature ice around 20 Kelvin. And what they saw is that when you went down to low enough temperatures, all of a sudden the radiolytic fragments of the water molecules all start to build up. And these build up very rapidly. And this actually causes an expansion of the ice layer that makes the diffraction pattern more blurred, but it also contains components of these radiolytic fragments inside of it, which is what's causing that blurring of the ring. And so we think that what you're actually looking at there is not water at all anymore. The shift in the pattern is all the things that are building up that are no longer water because they've been broken by irradiation. Whereas at liquid nitrogen temperatures, these are still mobile, so they go away or they move around and they are lost. Okay, so having delved into the physics of this and said, look, this is not a phase change, this is not a showstopper, it must be something else that's making our images worse. What is it? And more importantly, can we use some of the technology that we developed at liquid nitrogen temperatures to fix whatever this problem is, whether it's, charging or movement or otherwise? Well, one of the technologies we spent a long time developing for liquid nitrogen temperatures is the specimen support. And our latest generation of specimen supports, which we call a hexafoil, is simply a gold foil which has a pattern of nanoscale holes, in this case 200 or 300 nanometers in diameter, which you can put plenty of proteins inside of. And when you use grids like this in modern microscopes, none of the particles within them move by more than an angstrom during irradiation. And that's because we got rid of all of the other things that were causing motion and charging and displacement of images in there. And that leads to better quality data, which is critical. Okay, so we spent years developing these things. Why don't we try these at helium temperatures? Does this fix the problem? Is the blurring of images at helium gone? Well, in short answer, no. So this is an image of one of these 300 nanometer holes at 30 degrees tilt, and I'll play the movie of it so you can see it's looping through. So at liquid nitrogen temperatures, this would be absolutely motionless. But at helium temperatures, it's moving, obviously. So something has changed here, right? And so what's going on? Well, we had to do a lot of experiments to actually sort this out. And I should say, by we, I mean actually Josh Dickerson, who's here in the audience, a PhD student at the LMB, who has now just moved here to Berkeley, did a huge amount of work to actually tease out what is going on at these lower temperatures that's causing this movement. And one clue was this. You can see this displacement difference at 81 Kelvin. So, you know, a hexafoil grid at liquid nitrogen temperatures, it's perfectly motionless. And you go to 13 Kelvin, you see it starts to move. This is the distance between gold nanoparticles. And another clue came from this experiment. If you look at different thicknesses of ice layer at 13 Kelvin, the thicker the ice layer is, the more the specimen moves. So it's something to do with the ice. And another experiment, which I won't show the data for, but if you get rid of the ice entirely and you use one of these small hole gold grids, the movement goes away. There's no movement. So these are all clues to sort of what's going on in this. But I think the one experiment that really made it definitive as to what was the problem is this one. So if you start to change the geometry of the gold foil and you go from a 1.2 micron hole at liquid helium temperatures, you see you have a huge amount of movement. And you go to 300 nanometers, and it is reduced, as you can see here. But once we got below about 100 nanometers, or even slightly less than 200 nanometers, the movement went away completely again. And then what you see at liquid helium temperatures actually matches what you see at liquid nitrogen temperatures. So ice thickness is clearly playing a role, and the size of the hole is clearly playing a role. So how do we put all this together into some, you know, proper understanding? Well, this is our theory of what's going on at helium temperatures. So in the top here, you can see your specimen support. You freeze it, and we've put gold nanoparticles inside of it. And when you put it in the microscope, you take it from liquid nitrogen temperatures down to liquid helium temperatures. And because of this, the density changes slightly, but because there's water on top of the foil, this actually causes a crinkling because of the differential contraction of the gold relative to the ice layer. And this can be released as soon as you allow the water molecules to start moving. But also, when you start irradiating the water that's within the hole, this expansion occurs because of the buildup of these radiolytic fragments. And then that causes buckling again. This thing that we finally got rid of at nitrogen temperatures came back to haunt us. And the solution to it was to make the hole smaller so that you can find it so that buckling could not happen again. So even once you built up the stress by having these radiolytic fragments, they actually could no longer, you know, cause a buckling event to occur. And then the motion went away again because you couldn't exceed that buckling threshold. So taken together, how do we fix this problem? Well, I hope will be lots of ways to fix this, but the one way we fixed it, you know, in the first instance is this. You make an even smaller hole to put your protein inside of, which has an aspect ratio now of not, say, 10 to 1, but 5 to 1. And you use a small beam so that you're not irradiating a huge amount of foil that has both water and gold with stress in it that gets released. So what does this look like? So this is a grid fabricated with 100 nanometer holes with a 600 nanometer pitch. So much like the one I showed you before, except the holes are 3 times smaller. And these are some gold nanoparticles inside. And here you can see the beam that we put on it on our old Polara. Only has 2 condenser lenses, so you see the nice fringe pattern from the condenser lens, and it's actually just larger than the hole. And these 2 things together were sufficient to allow us to actually determine structures where every single frame in a movie series was better at helium temperatures than nitrogen. And we repeated this for both apoferritin and DPS for several structures, and this means that you get higher resolution for whatever it is, you know, you're trying to determine. And the factor of difference actually matches exactly the factor that we measured in diffraction patterns. On our microscope at 14 Kelvin, that's about 1.5 to 1.6. So that shift here from 3.3 to 5.1 is corresponding to what we measured with diffraction. So now we're seeing in images what we saw in diffraction, which is this key thing that we've been hoping to achieve for some time now. Okay, so how do we tie this back into our mission, which is to improve Cryo-EM over the next 50 years? So a few years ago, Richard and I came up with this, what we called our rough theory of all the things that we could think of that were making Cryo-EM images worse as a function of dose. And we called it at the time the rough grand scheme because we hadn't measured a bunch of these things and we didn't know exactly what was going on, but we had measurements of how bad the B factor was as a function of dose and from all of our movie data. And the small holes and all the other work we have done brought us to the point that at liquid nitrogen temperatures, we can actually get to this limit that we thought we should have, nice, smooth decay due to radiation damage. And so now we've revisited this theory and included the effects of the reduced effects of radiation damage at liquid helium temperatures and shifted it again. So part of what Josh's tour de force during his thesis was to actually, all of these measurements, which were many papers actually, to measure each one of these individual things, he repeated all of them at helium temperatures. And so we verified all of this at liquid helium again. And the conclusion is that over several different structures at liquid helium temperatures, we get better data in every single frame of every single image, which means that this is just not something we can leave behind in our field, because this will allow us to solve smaller proteins, more difficult structures, and all of the rest of it. Okay, so I'll just return to one figure that Richard showed earlier, which is the distribution of structures in the PDB done by EM. And you can, as he mentioned, we think, one of the frontiers of cryo-EM is to push this as far down as possible. And there are several things that can contribute to this. Liquid helium is one of them that I've told you about today, and it could contribute a factor of probably 1.5, possibly even 2 if you were to go to lower temperatures. But we need more experiments to actually find out if that's true, if we're going to go any lower than 14 Kelvin. But liquid helium is one thing, or liquid helium type cooling, even if you don't use liquid helium. Phase plates is another one, of course, that we just heard about, which we're very excited about and we think should benefit single particle as well as in situ imaging. Better detectors, of course, we're going to hear about next, which will certainly be important. We think, for many reasons that I didn't talk about, that lower voltages are really going to be better for determining the structures, especially of small molecules, because the smaller the molecule is, the lower the voltage you should probably go to in order to get the highest resolution and or even solve it. And then we've heard about time-resolved cryo-EM, which is very exciting. And then this is the key thing, I think, and Bob has been the champion of this more than anyone, that what we have on the grids is just not what we have in our test tubes. And if we could solve this problem, we would actually get orders of magnitude of benefit. And I think Ava, pointed to that earlier, and all of us who are doing this know this is true. And so a lot of our efforts also are towards trying to figure out what we can do about this, so that we would get rid of this problem of just not being able to solve the structure because of something that's happening as we make our specimens. So if I come back to the title of the meeting, the next 50 years, I'm going to start with another 50-year plot. So here is, back to 1975, and this is Moore's law here, right? So this is the number of transistors per CPU, and this is what's been driving technological innovation throughout the world, throughout humanity for some decades now. And it's an exponential increase in computing power, but it's had tremendous ramifications on all aspects of society, of course. And another, sort of exponential growth in science and technology and also in humanity is DNA sequencing. So this plot here in the blue triangles is actually the number of bases that you can sequence for $1,000. And I made up this first point here. This is Fred Sanger sequencing at the LMB, the first sequences that were done. But you can see, once people really started to put a lot of time, effort, and talented work into developing this, it was on an exponential trajectory for many years. And then it went super exponential, actually, and now it's up to amazing values. The number of bases that you can have sequenced is incredible. If we now come closer to home in structural biology, if you look at the number of X-ray structures that have been solved, it was on an exponential trajectory for quite a long time, a couple decades, but it did plateau, and now it is in decline, clearly. Whereas cryo-EM has now been on an exponential trajectory for some 10 years now. Indeed, tomography is also on an exponential trajectory, but it's an order of magnitude or more behind single particle. But if we do some extrapolations here, provocatively with the 2065 date, why not, right? But yeah, so more seriously now, how many structures do we really need, right? How many do we really need? This is an important question, I think, actually, you know. It's a lot of time, effort, you know, a big part of my life is spent trying to fix these problems. So, you know, do we really need more structures? So here's my rough calculation on the plane. So one genome right now, which is say 10 to the 9 base pairs, costs $100 roughly now, you know. And it requires absolutely no skill. You just stick something in a box and, you know, you get an email, right? That's and I say this because I did spend 10 years working on DNA sequencing technology. So I know, I know what went into making this, you know, no skill. So, you know, in 50 years, surely it'll be less than $10 to get a genome. But, you know, one cryo-EM structure right now costs $50,000, and that's for, you know, state-of-the-art equipment, people who know what they're doing, et cetera. So that's still enormously expensive because, you know, you can sequence 10 to the 7 genes for one structure. I think that ratio is way out of whack. I think we need to have a lot more structures for every sequence in order to keep biology and medicine progressing at pace to keep, you know, keep up with what humanity needs. So I think we should be able to, you know, we want to have sub-$100 structures, you know, within 50 years' time, and hopefully even sooner than that. And that would cause another revolution. So, all right. So anyway, I leave you with that. I thank a lot of the folks in my group at the LMB who make all this possible. I want to especially thank Josh Dickerson, who did all of the work I showed you here, Richard and Greg, who've been working with me on this 100 kV project for many years. And I'll point out one other person. This is Bob Morrison, who you may not know, but has been in the field for also some 40 years now, designing cryostages in many of the microscopes that you have had. And in fact, he designed the liquid helium stage that's in the Polaris, and in his retirement, he managed to come back and work with us on this project. So we were quite thrilled to have him. And then one final little thing for Bob here. So this is something from a Gordon conference in 2016 in Hong Kong. I think was chaired by Yifan, and we took videos which were cameos for a skit, which was a bunch of sort of entertaining jokes, but it sort of captures the positivity of Bob, you know. And I have to say, Bob, if it weren't for advice from you when I was a young grad student who knew nothing about this field, I never would have started working on cryo-EM. So I am entirely grateful to you for that and for advice for many years. Right. Thank you.
Thanks very much, Chris. I should have given you advice. Get out while you still have a chance. You're welcome.
Yeah, fantastic talk. Thank you. I'm really surprised about the price, the cost of an EM structure in 2025. What goes in there? Is it the cost of the machine, or what?
Well, the cost of the machine is the biggest part, the cost of the time of the people, but the biggest cost is the fact that even though, you know, a cryos can solve, you know, an apoferritin structure in a matter of minutes with modern technology and, you know, and computation, it actually takes more than, you know, 50 or 100 cryostays to get a structure because the specimens are bad. And I think that feedback loop is the biggest gap, actually. So that's why specimen preparation is the key problem of our field. But all of these technological developments will make everything easier. So we have to have all of it. And then if we solve the specimen preparation problem completely, then it could all be automated. It can turn into what sequencing is now, where you don't have to think about solving structures anymore. But we're certainly not there yet. So we've got a lot of work to do, I think.
So the service contracts are probably part of the problem here.
Well, the service contract is some fraction of the upfront cost, and then, you know, so the more expensive the microscope is, the more costly this is. So, you know, we certainly need cheaper microscopes, and I have no doubt that's possible.
This will be the last one.
Okay, so you mentioned about the radiolysis effect on the ice. So is it still diffuse, or is it just making heat so that the ice deform?
Well, you have to distinguish between when the beam is on and the beam is off. So when the beam is off, I think at liquid helium temperatures, nothing is diffusing anymore, or almost nothing. As soon as you turn the beam on, you induce pseudo-diffusion of the water molecules because they all start moving around, and then anything can move in principle. So I think that's the key distinction. You can never stop moving completely as long as you're irradiating the specimen, but when the specimen is not being irradiated, you can actually freeze out the diffusion of products, and that's what's going on here.
Okay, we move on to the final speaker in this session, Peter Dennis, on the development of cameras. Camera development really is what made the revolution happen, but we still have miles to go before we sleep, as the poet said. And Peter is going to tell us what we can expect to see in the near future. I don't know whether he's going to extrapolate to 50 years from now. That would be too much. Thanks.
I'm the last talk before lunch, so I'll try to be brief. So here's a conventional experimental setup with a source, an accelerating source sending a probe onto this sample with its positioning system. We want to minimize the number of probes that we use because of sample damage, so we want high efficiency. We definitely want to avoid false hits, and spatial resolution is a premium. So taking plus minus half a century of cryo-EM electron detection, if I go back sort of 50 years, we have alkali halide grains in emulsion on acetate, also known as film. It's wonderful because it's a digital detector. A film grain is flipped or it's not. Has various properties, lots of pixels, decent spatial resolution, so-so quantum efficiency. In terms of its temporal resolution, it's a little bit poor. That was advanced by various other forms of now analog detectors that happen to be able to plug into your computer. Phosphors that are fiber coupled to CCDs, which now have given way to direct detection CMOS sensors. And then 50 years from now, I don't know exactly what it will be, but it'll do everything. There are a lot of pieces involved in taking a picture, and I'm only going to talk about the part that actually takes the picture, which is the sensor. So I'm going to spend a fair amount of time on what the challenges are and how we can overcome the physical limitations for electron detection. And this is, of course, a long story that many people have been involved in, so I'm just giving sort of my perspective. So let me start with just how do we detect something. So we have some sensing medium. Our electron comes in, it deposits energy by ionization at some rate, dEdx. We collect that, integrate it over the path length of the electron. That amount of energy deposited has to be above some threshold to make it detectable. How much it deposits depends on the material. And then there's a position error that's limited by multiple scattering. So if we have a thick sensor that contains all of the energy, then depending on the energy of the electron, if you notice the energy scales and the distance scales, a bunch of electrons come in, they will make this blob that has a radius proportional to the range r. And as the energy of the electron goes up, the size of this blob goes up. The good news is we get a lot of energy because we get all of the energy that was deposited, but the bad news is that the multiple scattering, how big this blob is proportional to the energy. Now, to date, we project the energy deposited onto the entrance plane. So here's an electron, comes in, it does something, and we project onto the entrance plane all the little bits of integrated energy that have been deposited. And the position that we think the electron came in is wrong by some error, and that depends on this kind of energy-weighted path length. And that position error is proportional to the thickness of what we're collecting the energy over. So the thicker our detection material, the worse our energy resolution. And once we start to pixelate it, it doesn't get any better. If we have a thin sensor, we don't collect all the energy. And in fact, the distribution of the energy has this long high side tail following the Landau distribution that gets worse as the material becomes thinner. You can always lose more energy. The projected exit of the electron in this thin material has a displacement given by the multiple scattering. That displacement is Gaussian, and it goes like 1 over the energy, 1 over the z of the material, and it increases like the square root of the thickness. So our constraints now, in terms of what we want to use to sense, are these things up here. And the number of resolution elements, so how many real pixels you have, no matter what the marketing material says, is going to go like 1 over this position error that depends on these things here. In units that are normalized by density, the energy loss, so 1 over the density times the energy loss, or the range times the density, all materials are basically the same. So it says we want something dense. So how do we overcome this? Well, a logical solution that came from Ken Downing in the building next door was to, instead of trying to tame the electrons, make the microscope, design it for the electrons instead of the detection energy of the electrons, instead of the other way around. So slow them down. And that takes this picture and turns it into this picture. So that's a good idea, and it overcomes this limitation of multiple scattering given by the energy. But we can actually do better in a thin sensor because that multiple scattering is now going like 1 over the energy. So direct detection, you've heard, so what is it? If the electron goes into some sensing medium, it deposits energy, it creates some number of detectable quanta that depend on this, how much energy it takes to create one. If that then goes through another conversion process, so maybe you're making light, and it turns into electron hole pairs in a semiconductor, that's an indirect detection process. Same with film, you look at film. In something like a scintillator, it typically takes 10 or tens of eV to create a scintillation photon. If this is now a semiconductor, then you directly detect the deposit energy. It takes a few eV per electron hole pair. Either one of these methods, both of which are used in EM, depend either on the charge-coupled device, which was from 1969, or 1 year earlier, the CMOS image sensor from 1968. So the past sort of half century over 2 has used these devices, and I'm going to go out on a limb and say that at least for the next half century over 2, I think we're going to make use of these microelectronic image sensors. So the CMOS image sensor-based electron sensor rips out the camera from your early cell phone and passes electrons through it. So your cell phone camera is just an integrated circuit. It's got some wiring. It's got this region of moderately doped silicon. It has this region of very heavily doped silicon. And what happens is that the electron is depositing energy everywhere, but the energy that's deposited in this very heavily doped region, the charges that are created immediately recombine because of the high doping concentration in the silicon. So you don't see them. So you only collect charge from this thin region. So even though everything looks like a mess, you're only seeing this small part. And that's one of the things that makes the CMOS image sensor attractive for electron detection. One other little detail, just to make it work pretty well, is to get rid of any potential backscatter by hacking off any remaining silicon that's there, so that this picture turns into this. And that has turned out to be useful, as you probably know. Along with these came the notion of counting, which is sort of badly named, so let me explain what it is. Here's some energy deposition in some number of pixels. If you had a kind of X-ray counting detector, then you would set a threshold, and if the energy in this pixel, the charge of this pixel went over some quantity, then you would say, I have a hit. And you just count those hits, 1, 2, 3, 4, and that's a conventional counting detector. Works great for X-rays. Electrons are kind of messy, so where exactly do you set the threshold? Well, if you set it lower, then you get many pixels that light up. So that's maybe not so good. And as I don't have to tell you, TEM electrons are special. There's a large community of interest that worries about this extremely tiny region of the electromagnetic spectrum that's very colorful here. The challenge they have is that the absorption length for a photon varies over many orders of magnitude. Using X-rays, you've got pretty much the same variation, but over a much larger region. And 1 angstrom X-ray, which is just another way of saying a 12 kilovolt electron, makes nice little, very isolated things in your sensor as opposed to the mess that a 300 keV electron does. And if you go to higher energy, things just go straight through. So electrons are different from visible photons, X-rays, high energy particles. They're their own thing. So now, if we don't count the charge, but we integrate it, so we reproduce this pattern, then we can get sub-pixel resolution by taking into account all the different energy depositions, and that's accurate up to the limit that these differences are actually generated by multiple scattering rather than just collection of charge. So to make this work, there's a trade-off between occupancy and speed. If you have 2 electrons that arrive at the same time and are a bit hard to tell apart, then you can't really tell if you have 1 or 2, just have a blob. But if you're fast enough to be able to separate those 2, then you can easily tell the difference. Now where counting is different from just integrating is that if you simply integrate signal, like film, like your camera, then what you see is the point spread function in the sensor for each one of the charges, and that's the pattern that shows up on your pixel. So you very much want to have a point spread function that's smaller. But when you count, you don't care about what the point spread function in the sensor is because you're actually using that information, and you're either just assigning each position to a mythical Shannon pixel, this pixel is hit, or even better, saying I've localized to within the spatial resolution of how well I can count, not the spatial resolution of how the signal spreads in my sensor, and that's how well my sensor can do. So for me personally, looking at some sensor developments over the last 10 years, I was very focused on speed. Speed is useful for the reasons above, but more recently on some other improvements. So one of which is to go to the kind of cell phone camera you have in your phone now, assuming your phone is at least as modern as this iPhone 4. And that's one where instead of going through the wiring end of a sensor into the active region with some more material, you shave all of this off, turn it upside down, go directly into the sensitive volume, and that means at high energies, you get rid of some of this initial scattering, but this becomes more important as the energy goes down, because the lower the energy is, the more scattering there is in this dead material, up to the point that you may absorb all the energy and not even see a lower energy electron. When we first did this about 10 years ago, it was a very artisanal thing in the lab, but thanks to these kind of commercial pushes, this technology is becoming more readily available, and electron detectors that are back illuminated are starting to become commercially available. So that's one improvement. Perhaps the largest one is in sort of how we collect the charge. So what's the limitations to spatial resolution come from the multiple scattering, the charge collection, which I'll describe in a minute, signal to noise, and other things like backscatter into the detector. So here is our pixelated detector. These are pixels. Each one of these is collecting charge. This is the volume in which the charge is being generated. As the electron comes through and it scatters, it creates electron hole pairs that are kind of scattered around this pattern. If those charges then have to somehow travel to the electrodes they're being collected by, and the better we can concentrate that, the better we can do in terms of spatial resolution and signal to noise. And then we just generally want to improve the signal to noise of the whole detection process. So most sensors today, what's in your cell phone, collects charge by diffusion. So there's no net electric field here. So these charges have no reason to go one direction or another. So they diffuse into 4 pi. It ends up working out okay because this layer is quite thin, but it means charges diffuse. If you can create an electric field here, then these charges will drift in a straight line, and so you collect them better. Doing this depends on changing dopant concentrations and a bunch of other details, so it's typically not done. So almost every sensor collects charge by diffusion, but we can gain if we can collect charge by drift. And here's an example. So these are some electron images in a sensor that collects charge by diffusion or charge by drift. Same vertical scale. And in both cases, looking at this plot here that sums over larger errors, you always get all the energy. So you collect all the signal from here just as you collect from here. But as you can visibly see, it's a lot easier to see these guys, and they bleed out a lot less than this. So this is kind of a new avenue to try to improve what exists now. That lets us re-optimize thin sensors from the original ones that were in kind of electron cameras now. At the moment, although the amount of energy we get goes like the thickness, the problem is the diffusion does as well. And if you make a sensor that collects by diffusion thicker, you end up often losing faster because, yes, you get more signal, but it diffuses over a larger volume. Whereas if you collect charge by drift, you just get more signal. So again, these are the things that are limiting us. We can overcome this by doing drift. That helps with signal to noise, helps our detectability, and then we can now optimize to get a sensor that does the best it can for multiple scattering for a thickness that that maximizes our signal. So to summarize all of that, multiple scattering is a fundamental limit to spatial resolution. The signal to noise in terms of this quantity eta and ddx, and readout noise is a fundamental limit to detection. Everything else is kind of negotiable. So we're going to put we're going to put these new developments to use in supporting the development of continuous tilt electron tomography that David Agard and colleagues are doing at the CZ Imaging Institute. And there was kind of a wish list, please do this. And the this ends up needing something that does 2,000 frames per second with 100 million pixels in it. So it turns out that's a lot. So the problem when you just say more pixels, please, is that the speed challenge goes like the square of the size. So 100 million is a lot harder. It then turns out that if you want that with a lot of frames, it's a lot of data. So this is 0.2 terapixels per second. So that's kind of a lot. So that's a big step over what there is today. But we think we have a road to get there based on these kind of improved pixels that gives us better performance and lets us go faster. So we are in the process of making a first step that's a quarter of a way to this that we have named Celtic for cryo-electron tomography initial camera. Backside illuminated, does this stuff, and we'll be ready this year to try and help facilitate the development of this continuous tilt cryo-ET, which may have other challenges just besides the detector itself. Now I should mention, in addition, hybrid pixel sensors. Hybrid pixel sensors were developed for particle physics starting kind of very late 80s, early 90s. They were spun off quite successfully for X-rays. Before people tried CMOS image sensors, they tried, very close to here, hybrid pixel sensors. Oh, and I should say a hybrid pixel sensor is a dedicated sensor layer that is connected with solder bumps to a dedicated readout chip. The pixels are big, but you can cram a lot of intelligence into each pixel. So these have certain advantages because they're smart, but they're thick, so charge is big for electrons, and you don't get very many pixels because the pixels are big. This kink in the slope, we've seen this picture now in many different forms. So the kink in the X-ray slope comes from when hybrid pixel sensors for X-rays start to become available. And as well, the slope, not even the kink, comes from the CMOS image sensor pixels becoming available. So what's going to happen a few years from now? I think in terms of imaging, to get many, many pixels within the optically usable field of the microscope, it will still be kind of what we're doing now, a thin sensor with the number of resolution elements limited by the spatial resolution. So there's still some blood to be squeezed out of the CMOS image sensor turnip. An intriguing question is, well, if we do diffraction, if we do scanning microscopy for biology, does that do the same dramatic things it does for material science? We don't know yet. If it does, it doesn't take as many pixels by a lot. And it also allows for a different optimization for what is the right STEM detector for hard materials or soft materials. It's a little hard to talk about 100 years of history of electron cameras, but we can talk about 100 years of history for this very limited wavelength region of visible light cameras. And so this shows cameras for photographic film, which then got replaced with charge-coupled devices, and then got replaced by these CMOS image sensors. But this is actually the plot. I chopped it off here. So these are the CMOS image sensors. This is photographic film. So we're kind of, I think we're backing the right horse. So what are these visible light people doing now? Well, a lot of what has been done is processing of the semiconductor to improve the capture of visible light. Does nothing for us. But an interesting thing is they are going super hybrid by the use of 3D integration, which allows connecting different pieces of silicon at very fine pitch. So this is a nice thing from Sony. So this is a 3 completely different layer camera that still has a CMOS image sensor. It has a bunch of DRAM down here, and it has a processing node. So this definitely makes for a better camera. Not clear that it makes for a better sensor. And I'll just mention that the reason Sony developed this was so that they could get something that would go at 1,000 frames per second. So they developed this for speed. Interesting for many things, may not make a better sensor. So 50 years from now, what are we going to do? So first, I start with the very well-known sensor designer Wallace Simpson, who said you can never be too thin or too rich. Now, of course, what she really meant, we know what she really meant. What she meant is that the ideal imaging sensor is as thin as possible with the highest density and the lowest value of eta. I'm sure that's what she meant. So that's one approach, and that's probably true. But, and if we look, for example, at a superconductor, in our semiconductors, we need EVs to make a countable quantum. And in a superconductor, we need millivolts. So maybe we should be going cold. Now, maybe this is also old-fashioned, and what we should be doing is instead of making pixels, making voxels, and finding some way that we can track electrons in a thicker sensor. There were attempts to do this kind of thing for visible light, to discriminate between different colors. Didn't work so well, but OK. There's 50 years, so we'll see. I'm not sure which of these will be the solution, if any, but I will come back in 50 years and let you know. So for 50 over 2 years, a lot of people were involved, which I definitely have to thank. And at least for me, I have to point out this very sort of catalytic workshop from some time ago that was a very nice look from the top to the bottom of the electron microscope on how to make it better. And that certainly was important for me. So I thank you and happy to answer any questions.
Thanks so much, Peter. Super. 1 or 2 questions, because the only thing standing between you and lunch is...
It's all good.
But a couple of questions, please.
People are starving.
I was curious, what would happen if you just took a regular cell phone camera sensor and tried to use it as an electron detector? What aspects of those cell phone cameras don't work for electron detectors?
So the same way that your biological specimen does not like sitting under the same way that your biological specimen does not like sitting under a continuous beam of electrons, neither do pieces of semiconductor. So a lot has to be done, and there are, in fact, some compromises that are made in order to make the sensor be able to stand up to the beating it takes from the electron beam.
Sorry if I missed it. In the end, what happened to the idea of decelerating the electrons? Was it just not worth the effort because the anticipated gains wouldn't get us far enough, or is there some fundamental reason it shouldn't be done?
There's nothing fundamental. It's technically challenging. Takes a big volume of space. You unfortunately have to float your camera at several 100,000 volts, so that's a bit of a challenge. But then it I think, does turn out in the end that a thinner sensor actually can do better. But the idea of thinking about the microscope in a way, how can we optimize it for detection, is absolutely a valid idea still.
Well, one last question from Chris, and then Eva has an important announcement.
Quick one, Peter, thank you. In 50 years' time, would it be possible to make a 100 keV pixelated detector with 1 eV energy resolution by any way you can imagine?
So yes. So the energy resolution. Now, okay. You said by any way I can imagine. So what we don't. I don't know what energy is. I only know what countable quanta are. So I get some number of quanta that depend on this thing, and the problem is this value has fluctuations called the Fano factor. So there's an intrinsic limit to resolution that all depends on this. So if we get enough countable quanta, that gives you the energy resolution. Now, I'll just make the note that the one thing that I will have to hand our X-ray friends, even though you did send them kind of down into the ditch, is that they're kind of pretty good at getting decent energy resolution, but in principle possible. And for example, what people who make superconducting detectors, their whole argument is energy resolution. 1 eV, okay, we'll talk, but.
Well, let's start. So you may have noticed we've eaten halfway through the lunchtime, but we'll move the starting time by a little bit, maybe 10 or 15 minutes, so that you have time for that. But also, there will be a presentation about 20 minutes or so, but one of our sponsors, Thermo Fisher, during the lunchtime, so you can maybe go grab some food. Maybe if you're very, very careful, you can even bring it here and you can listen to that if you want. Otherwise, just remember, we are recording all of this and you will also have access to it later on. But just be aware, we'll run around just telling you that the talk by Thermo Fisher has started and please be aware of that. Thank you.